Hello everyone, my name is Vo Ding Cong Tinh. Today I would like to introduce about the topic chemical sustainable fuel cell via layer by layer fabrication of sulfonated polyethylene ether sulfone membranes containing serum oxide nanoparticle. As you know, the serum oxide is an excellent candidate to capture the radical in the fuel cell application. However, the serum oxide is a muted conductor materials which can transfer both the electron and proton. But in the fuel cell, if the electrolyte membrane can transfer the electron, it will decrease the performance of the system. In this topic, I would like to apply the serum oxide to the surface of the SBAES membrane to prevent the electron transfer ability of the serum oxide. And on the other hand, in order to improve the anti-oxidation stability of the polymer, the sulfonated polyethylene ether sulfone group, the sulfonic acid group by the sulfide bonding, was prepared in my study. And this sulfide bonding thus can make the bonding with the radicals and to form the sulfone bonding, and sulfone bonding that is very stable in the fuel cell condition. And this is the process how I can repair the layer by layer membranes. I will spray the SBAES solution containing 2 or 4% of the serum oxide onto both the surface of the pristine SBAES membrane. And this is the process how I synthesize the SBAES polymer and the serum oxide nanoparticle. And if you are interested with my topic, you can read clearly about that in my paper with the same title. And this slide is the physical chemical property of the serum oxide nanoparticle. We can see that the diameter of the serum oxide is about 7 to 5 nanometer, and it's very uniform. And moreover, from each of the spectra, the serum oxide is the spherical nanoparticle, and we can see the same behavior in the same image. And next slide, that is the NMR, FTIR, and XPS spectra. And from all that result, that can confirm I already synthesized successfully the SBAES polymer with the sulfonic acid group at the binding site. And the chemical stability of the membrane is a principal property of the membrane because it decides the long-term stability of the membranes. We can see the figure A, that is the phantom test result. We can see the residual weight of the membrane drop with the increase of the sulfonic acid group concentration. The reason is when we increase the sulfonic acid concentration, the hydrophilic stability of the membrane will be increased. Thus, the radical will easily come to inside of the membrane and attack in the polymer structure to degrade the polymer structure. So, and when we compare between the same 140% of the sulfonic acid group, the residual weight of the membrane after phantom test increase with the result of the serum oxide. Moreover, figure B is the OCV test. OCV test also confirm the membrane containing 4% of the serum oxide still work very well after 500 hours. Meanwhile, the SBAS 140 or the nephew membranes were decayed after around 200 hours. And figure C and D is the sulfonous emission rate of the membrane up at the anode and cathode side of the fuel cell system. We can see the sulfonic emission rate of the layer by layer membrane is significantly lower than that of the SBAE S140 membrane, and this result can demonstrate that a part of the radical generated at the electrolyte was scavenged by the serum oxide in the both surface layer of the membranes, and another result is the reuse image or and same AFM image of the SBAE S140 and layer by layer membrane containing 4% of the serum oxide nanoparticle. We can see the principal membrane is easily broken after 12-hour treatment in the phantom test solution. We can see in the figure E and J. However, with the membrane containing 4% of the serum oxide at the both surface, we can see it's still very stable after 12-hour treatment in the phantom test solution. And figure L and M are the AFM image of the SBAE S140 and layer by layer membrane after 6-hour treatment by the phantom test solution. And in the surface of the principal membrane appear a lot of pinholes. Meanwhile, the surface of the layer by layer membranes just appear a few. That means in the pristine membrane that's a strong degradation, but the membrane containing 140 the membrane containing serum oxide at the both surface layer that is still very stable. And the last one, that is the performance of the fuel cell. The figure A and B is the performance of the membrane with different content of the sulfonic acid group. The membrane containing 160% of the sulfonic acid group show the highest power density, and the lowest, that is the SBAE S120. And figure C and D are the performance of the layer by layer membrane and the composite membrane containing at the same amount of the serum oxide. And from this result, that is the reason why I want to repair the layer by layer membranes in this topic, because we can see the composite membrane containing the same amount of the serum oxide nanoparticle is so the very low the power density. The reason is in the composite membrane, this is containing serum oxide. This serum oxide, it can transfer the electron through the membrane. That will be decrease the performance. However, in the layer by layer membrane, at the between layer, that's only polymer. So that means that will be prevent the electron transfer ability of the serum oxide. So the electron that is too difficult to transfer through the electrolyte membrane from anode to cathode. And figure E and F is the performance of the SBAES and layer by layer membrane containing 4% of the serum oxide after 100 hours of the OCV test. We can see although they show the similar power density before OCV test, but after 100 hour treatment, the layer by layer membrane show the power density that is higher than other. So that means the chemical degradation of the layer by layer membrane containing 4% of serum oxide is the lowest, and and we can show the we can see the performance of the serum oxide nanoparticle to scavenge the radicals. And finally, that is the conclusion. The first, that is a series of the SBAES polymers show the low water uptake and swelling ratio, but it is high conductivity at around 100% of relative humidity, and the serum oxide phase with the nanoparticle size around 5 to 7 nanometer was successfully synthesized, and proton conductivity that's of the membrane containing 4% of the serum oxide nanoparticle, that is not significant decrease when we compare with the pristine membrane, and the layer by layer membrane containing serum oxide can block the electron and oxygen transferring through the layer by layer membrane. Thus, it conserves the performance of the membrane out of the negative effect of the serum oxide. And the last one, that is the installed oxidation stability and OCB test. So the chemical stability of the SBAES 140 containing 4% of the serum oxide at the Bose phase was the highest amount of the membranes. Thus, the layer by layer membrane containing 4% of the serum oxide nanoparticle had the high potential to apply for electrolyte membrane in the fuel cell application. Thank you so much for your listening.